All right. Ready to start? All right. So, welcome. Yeah. My name is Odin. I come from the consultancy Kodemarked. And my fascination with crypto started some years ago. I bought some Ethereum for $10, and I was really happy when I sold it at 20, 100% return on investment. Sometime later, the value was almost $5,000. But hey, it's not like I'm bitter or anything. So today I'm going to talk about a pyramid of dumpster fires. That is like Web3 is a controversial subject, and it involves crypto and blockchain technology, and that's an area that's full of scams, pyramid schemes, and hype. But I will not deal with that today. Let's just put that aside, and what we'll do instead is to just look at the technology itself and to see how it really works, and from a developer's perspective. And we will try to figure out if it's as good as people say it is. My goal with this presentation is that when you leave today, you will know more about what a smart contract is. And I think this is important in this day and age because it enables you to form your own opinion and to ask critical questions about a technology that promises a lot. And especially when you add like large economical value into the mix, it's really easy to lose your head and just not think clearly. So first, I'm going to define Web3. Then I'm going to take a closer look at blockchains. And then we're going to get to smart contracts. I'm going to show you a couple of examples, one of which I made myself, which is a Tamagotchi that lives on the blockchain. Sounds really weird, but I will show you. And lastly, we will look at how to actually develop smart contracts. But first, let's define Web3. There is no clear definition that everyone can agree on here, but here is at least one way to explain it. It begins with Web 1, and that is the open internet of the 90s, where you have like open, decentralized protocols, and the users, they typically consume content from static web servers. And then we have Web 2, which is the internet of the 2000s, with the huge centralized platforms like Facebook and Google, and where the users typically produce the content for these platforms so they can make money. Web 3 is going to be like a solution to this, where we're going to go back to the open, decentralized protocols, and the users are going to take back control. They're now able to own their own stuff and also participate in the governance of the thing. And this is going to be done with blockchain technology. All right? But what is a blockchain really? I will only give like a high-level description here. It's really easy to get lost in the details, and there's a lot of interesting technical stuff to really dig into here. But there's also a lot of terminology and buzzwords. But I will only cover enough to like get an understanding of the basics of this technology to better understand its constraints, and that is important. So, what is it? Well, at its core, it's just a database. You can write and you can read data from it. But importantly, it's a decentralized database. So there is this network, like a peer-to-peer network of computers, and every node has its own copy of the database. And then there is some kind of rule or algorithm that enables you to write to the database. And a critical aspect here is that it's an open system. Everyone who wants to can participate. So you don't need to be given access by like a centralized party to play along. It's a really slow database as well. So Bitcoin can do about 7 transactions per second, and Ethereum, which I'm going to cover in detail here, can do about 15. But there's something more important to consider, and that is the confirmation time. So in Ethereum, it takes 5 minutes before your transaction is confirmed. And what does that mean? That means that you will have to wait 5 minutes in order for you to know that your transaction has been accepted by the system and written to the database. Just think about that, 5 minutes. It's an expensive database as well, so depending on the amount of traffic on the network and like what you actually want to achieve, you'll have to pay somewhere between $1 and $20 minimum to do one transaction. But how can we get the nodes in the network to agree about the state of the database? Well, this is where the consensus algorithm comes in. And we have to consider malicious actors here as well. There might be someone that tries to steal your, or like subvert the system somehow. So how can we reach consensus in a distributed system? We have the classical algorithms, but those have a couple of constraints that are not good for us in this kind of crypto blockchain world. And that is that every node has to know every other node, and also every node has to talk to every other node. So this only scales so far. So we can't use that. This is where proof of work comes along. So this is like the original crypto consensus mechanism that was introduced with Bitcoin. I'll try to explain that now. How does that work? Well, here we have Alice. She is sitting on her computer. She's not connected to the internet or anything, and she wants to create a wallet. The only thing she has to do is to generate a public key pair, and she just needs to keep her private part secret, right? And then, by using that key pair, she can derive an address, and with that address, anyone else in the system can send her value. And when she's ready, she can also transfer value to the system, and she does this by signing a transaction with her private key, and only she can do that. All right, but what happens with the transaction then when she's sent it into the network? Well, first we need to see what the data structure is, and that is a ledger. That's just a long list of transactions, and it's append only. You can't delete transaction from it. And here we have a network of nodes, or miners in proof of work. So the users, they send in their unconfirmed transactions into this network of miners. And it doesn't matter which miner they talk to. These unconfirmed transactions, they are like shared between the miners, and they go into what's called a memory pool. Think of it like a waiting room for unconfirmed transactions. But how do these transactions get out of the waiting room and into the database? Let's take a closer look at one of the miners. So this miner, he has a memory pool, and then he needs to figure out how to make a block. And a block, that has a certain amount of space. So it's not certain that he can fit all the transactions from the memory pool into the block. So how does he decide which transactions go into the block? Well, when you make a transaction, you can add a little fee, or that's like a little tip to the miner. And by using that, the miner just picks out the biggest tips. And then he gives himself a little reward for doing this. So remember, this block hasn't been confirmed yet, so this is just the starting point. So what happens with this block? Well, the miner, using the algorithm of the proof of work system here, he then starts what's called like a guessing game. This is where all the miners try to compete with each other. So how does that work? Well, we take the block and we put it into a hash function. And this is a cryptographic hash function. And that means that it's a one-way function. So you can't go from the result and back to the input easily. What does that look like? Well, it's just some random numbers. And the name of the game here is for the miner to try to figure out a hash that starts with a certain number of zeros up front. And like the goal of the system, at least in Bitcoin, is to do a block every 10 minutes. And whenever blocks are found too fast, they just increase the difficulty. And that is just adding more zeros to the requirement of the block. But how does he find this number? Well, this is where the work part of proof of work comes in. So the miner just has to insert a number as well into the hash function. And there's no way other than just trying lots of different numbers here. And this is where the miner has to spend a lot of CPU. The nice thing is that it's really hard to find this hash, but once you've found it, it's really cheap for every other miner to verify that, yes, this miner actually found the secret number. And that's the key here. And also, we tack on the previous hash of the previous block. And this is the blockchain. This is where that concept comes in. But why do we do that? Well, let's have a closer look at it. Here we have just a list of blocks. And let's say someone wants to delete the transaction that Dave did to Alice. How would that work? Well, by removing that transaction, the hash of that block will change. So then the miner would have to try to figure out that number. But also, it would also have to figure out the numbers for all the other blocks that point to it. So this is where the confirmation time that I talked about earlier comes in, right? You have to wait an hour. And the reason for that in Bitcoin is that you typically have to wait for 6 confirmation in order to be like sure that your block with your transaction is like piled on top of with as much CPU power as possible, right? So there's one last crucial piece to explain proof of work. And that is that the state of the database at any one point in time is governed by the longest chain that exists. That represents the chain that has the most work invested in it. Okay, so let's say we have a list of transactions here. And in the last one, someone has bought a Lambo, and it's been delivered. And then we have the miner who has the Lambo. He wants to like double spend his money. He wants this transaction to never have happened. So what he does then, here we have an evil miner. He then the only thing he has to do is just to create the longest chain, right? He just have to figure out the numbers the fastest. And the reason this doesn't work is that the amount of hashing power that all the good miners has to be like more than what the evil miner has, right? So in order to attack this system, you would have to acquire lots of hashing power. Okay, so proof of work solves a really hard problem, and that is how to achieve distributed consensus. And it does it in a really smart way, in like a technical, interesting way. So the problem here is, of course, is that the cost is really high when it comes to energy use. So it's not a sustainable solution, and everyone agrees about that. So we need an alternative. And one alternative is proof of stake. So actually, Ethereum, they just switched over from proof of work to proof of stake a couple of weeks ago. And then the world's energy consumption, it fell by 0.02%, which is like insane amounts of energy. So how does proof of work, proof of stake actually work? Well, there's no need to guess a random number anymore. So what's done instead is that in order to participate as a node in this system, to be able to write transactions to the database, they're called validators or stakers. Then you just have to put aside a certain amount of stake or tokens. So those represent an economical value, right? And by doing so, you have to lock them down, right? And by doing so, you are then enabled to participate as a staker. Okay, so here we have validators in a network. And all of them have locked down a certain amount of stake. And the more stake you lock down, the more often you get to write to the database and get a reward. And then there's some kind of algorithm that decides at given intervals who will get to write the next block. So here we have one of the validators. He has been allowed to read from the memory pool, create a new transaction block, and give himself a little reward. And then he updates his database, and then he ships the new block to all the other validators, and they update their database. So the security here lies in the fact that in order to subvert this system, you would have to buy a lot of stake, and that is really expensive. So we've solved the problem of energy use, but we have gotten another problem, and that is that proof of stake, by definition, means that the rich are now in control. just as with the centralized platforms where the rich are in control. Okay, that is a different discussion. I won't get into that here, but just think about that. So let's have a look at smart contracts. The name is really misleading because the contracts, they are not smart, and it's not a contract in the legal sense of the word. So it's just code that can be run on a blockchain. It can write and read to the distributed database. And it's kind of like a stored procedure, but not quite. So how to explain that? This is just a regular transaction. This is just a transfer of value from one address to another. A smart contract invocation looks like this. It is also a transfer of value from one address to the address of the smart contract. So you can actually send money to a smart contract. And then you can tack on some data, and this represents a function call. So this is a function call to do stuff to that smart contract, and you add some parameters to it. And that's it, really. It's not more complex than that. And now you have, of course, you have a virtual machine that can read this kinds of transaction and actually execute the code and update the database. Here's my attempt to explain what a smart contract looks like. So it has an ID, a unique ID. It's just a hash. And once you've deployed it, it can never change. The code is immutable. You can't change it. It has a set of variables that you can read and write to, and it has a set of methods. In this case, these are read methods, and those are free to invoke. Everyone can invoke them as much as they like. It doesn't cost you anything. However, if you want to write to the execute a write function, that costs token. And the price depends on how much data you're going to write, how much CPU you're going to spend, what the developer charges for that invocation, and also how much traffic there is on the network. But there's also a wallet, so that smart contract can actually store tokens. I will show you an example of that. So it's basically programmable value. That's the idea. Okay, so the smart contracts themselves, they live inside the distributed database. What does that mean? Well, it means that when you as a developer deploy your smart contract, the code is compiled to bytecode and it's shipped into the decentralized network. And to deploy, that costs you tokens because your code takes space. And the more code you write, the more expensive it is to deploy. And you have to pay every time you deploy. Everyone in the world can call the functions in your contract. It's totally open. This includes, of course, malicious actors. It might be that someone wants to actually steal the value that's inside your wallet, inside your smart contracts wallet. So making smart contracts requires a very, very high level of attention to security. And there's lots of examples of hacks, like millions of dollars lost there. The code itself, usually the serious programmers or developers here, they choose to actually publish their source code. But that means that the malicious actors actually can read your code as well as invoke all your functions. And that gives them a level of access compared to traditional system, which is just unheard of, right? So there's no firewall here, there's no monitoring, there's no nothing, right? You're totally in the open. So why would people choose to publish their source code? Well, your regular users also need to read your code in order to understand what your contract is going to do to their value, to the money, right? So smart contracts, they run in a really constrained environment. This isn't like a regular programming environment. What do I mean by that? Well, a smart contract can only access its own state. It can also invoke other smart contracts, but it has to be invoked from the outside, either by a user with a wallet or just a system with a wallet. You can't invoke yourself as a smart contract. That means you can't have a periodic job that does stuff to your smart contract, or you can't listen to events or stuff like that. That has to be invoked from the outside, from centralized systems. And you can't call out to external web servers. you can't fetch data from the outside, or you can't even like write data to the outside. You can, though, like emit events that external systems can listen to. So if you take a step back, that means that a smart contract invocation, that is like a pure function. It takes the state of the system and a transaction, and it produces the next state of the system. And this has consequences. It means that you cannot have randomness in smart contracts. It has to be deterministic. Why is this? Here we have a validator node. It has a new block to write, right? It's been elected to write the next block. And this block contains just transactions, and some of which are smart contract invocations. So what does the miner has to do to update his, the staker has to do in order to update his database? Well, he takes the state of the database and the list of transaction into the virtual machine function, right? And it emits the next state. And then he ships that new block to all the other validators. And the thing now is that what do they have to do? Well, they have to execute exactly the same code as the first validator. And they have to do this in order to verify that it's correct and to update their database. Right? This is why it has to be deterministic. If it was any randomness in here, you wouldn't get the same result across the entire network. And that would be a problem. So interestingly, if you take a step back, that means that smart contract invocations represents a single thread of computation across thousands of machines. So ironically, compared to traditional systems where you can scale by adding machines horizontally, you can't do that. There's no parallelism here. This is why blockchains are slow. Well, they are actually trying to figure this out and try to like scale this system. And there's like lots of different approaches here, like side chains, level 2, level 3, sharding, none of which are in widespread use. And common to all of them is that they complicate an already complex system. There's a lot of security pitfalls here, and it also increases the attack surface of the entire blockchain system. So by scaling, they typically also impose restrictions on the system as a whole that affect the usability of the thing. But hey, who knows? Maybe they will figure this out in the future. And as a side note, I know there are blockchains that have claimed to solve this, but they are not widely used, and thus you can't be sure that they actually work at scale. Okay, let's have a look at the Oracle problem. So this isn't Oracle, the software company. Then you have a different kind of problem. This is, it turns out that actually getting data, reading data from the outside world in a smart contract is really useful. And there are lots of examples of that, actually. So it might be that you want to like make a decentralized stock exchange, and then you need to have price data from the outside. And let's say you want to make an insurance contract where you pay farmers money when there's a flood, and then you need weather data. And let's say you want to have a will as a smart contract, then you need to know if people have died or not. And also just randomness, like getting that into the system is really useful. And this is called the Oracle problem. And the Oracle here, of course, is like the service that is the interface between the smart contract and the external world. So it turns out that you actually can do it by doing just this. Like you have an external service that's just a regular web server on the internet, and that just pays to put data into the system at regular intervals. Like write some randomness in every 10 minutes or something. There's actually also a way to read data on demand. So how does that work? Well, here we have a smart contract that you have made, and we have an Oracle, and it has some kind of data that you want. That's just a regular server on the internet. The Oracle has its own smart contract that it monitors for changes. So when you want to fetch data, you have to initiate a transaction from the outside, and you say, I want foo, and you have to pay for that, right? And then your smart contract talks to the Oracle smart contract and writes into its state, hey, this smart contract wants foo, right? And the Oracle sees that, and it writes foo, right? And of course, we can just skip all that and just pay the Oracle directly, right? to do the same thing. Yeah, we've solved the problem, haven't we? Well, except you have taken a decentralized system now and leaned it on a centralized service in order to do something useful. You have to trust the oracle, and that's just a server on the internet. It can go down, it can fake data, but most importantly, you have to trust a centralized service. So you have to wonder, why use a smart contract at all in this case? Okay, how does smart contracts work as seen from a user? I'll try to explain that here. So here we have, it's just a regular person with a laptop. It might also just be a smartphone, right? And he goes to xyz.com. That's just a regular web server, and it has some HTML on it and some JavaScript. And inside his browser, he has a wallet as well. I'll get to that, and I'll show an example of that later. And then the page is loaded in his browser, and during the initialization, there is some JavaScript library, typically, that will talk to the external system and the smart contract, right? Like this. And it will read the state of the smart contract, and then you can draw it in your browser. Doesn't cost anything, it's free. Everyone can do this. But let's say you want to update some data. How would that work? Well, let's say you click a button inside this page. Then your wallet is going to pop up and say, hey, this interaction is going to cost you so and so much. And then you sign it, and then you send your transaction to the decentralized system, and then you wait 5 minutes. Yeah. Okay. But I've lied to you. What is really happening here? There are some details here that are crucial to understand. You can't just trust a random computer on the internet. Your browser can't just talk to one of the nodes in the decentralized system. It might be malicious, right? So ideally, you would have to run your own personal node on a server that you control. And that server would run the blockchain software, and it will like sync the distributed database, and then your browser will have to be configured to talk to that personal node. But if there's one thing we've learned the last 30 years, it is that no one wants to run their own server. So, because you have to run it somewhere, right? You have to patch security updates, you have to keep it online, you have to have enough disk space, you have to pay for power. So, not even developers these days want to run their own server, right? So, it's just too much hassle. So, virtually no one runs their own node. What do they do instead? Well, they use a centralized service. Everyone does this. So there's a couple of companies that are really huge in this space, and basically everyone uses this. Even the wallets do this. When I discovered this was like a huge surprise to me. I couldn't believe it. Like so much technology and effort to make a decentralized, trustless system, and then we just throw it out the window and rely on a few companies without any verification. This smells like a lot like a Web 2 system. Yeah. And of course, this centralized service, it can see all your read transactions. So it's similar to like surfing the web through a third-party server that can see all your web traffic. Yeah. And why do we do this? Well, the API is faster, it's better, it has access to history and analytics. Yeah. My point here is that the dream of decentralization just isn't true. Okay, but let's look at something fun. This is an example of a smart contract. It's a non-fungible token. You probably heard about those. Here we have a smart contract that is an NFT. This is a picture, it's a movie, and it's also like a physical box that shows the movie. It's pretty cool, actually. And this was sold for $29 million. Okay, let's have a look at the technology behind that. We can see that there's a smart contract address here, and that represents the NFT. It can hold a lot of tokens, like different images and stuff, and we can see that the token ID in this case is 1. So just remember that. We need that later. How can we actually have a look at this smart contract? Well, there's this thing called block explorers on the internet, and that's just a service that runs a node, and it also has some kind of web service and database and stuff to enable you to search for transactions that have happened. You can find smart contracts. So let's just use one of those. We put the address of the smart contract into that, and we find the source code. And we can read that if you want. It also has functionality where we can actually interact with this contract. We can like execute, read, and write transactions here. It's kind of like Swagger or OpenAPI if you use that. So let's try to find the images. So we invoke a function, a read function that's called token URI, and that gets back a URL to just a regular web server. Where's the image? Well, it turns out that with today's prices, to store 1 kilobyte of data costs about 200,000 kroner. To store the image and the movie would cost you 7.5 million. And that's shy of $1 million. So that's insane. Nobody does that. So yeah, let's just point to a web server instead. Let's have a look at that URL. Here we can find metadata about the NFT. This can be anything really, but in this case it follows a certain standard that all the NFT sites can use to like list all the NFTs that's in a smart contract. And you can use this to like show an avatar on your social media page, whatever. The interesting part here is that we can find the image reference here. We can find the image and the movie reference, and that is also just a link to a web server. Okay, so what do you actually own when you buy an NFT with this smart contract? Do you own the image? Let's break that down. The picture file is stored on a web server, just a regular web server. The metadata, think of it as the sign that points to the image. That is also just stored on a web server. Like obviously here, the image can disappear, the servers can go down, someone can take over the domain. So this is not a good solution by any stretch of the imagination. And everyone agrees on that. But what do you actually own? So the URL is stored in the distributed ledger. So what you own is the sign to the picture. That's what you own. I'm not sure, but I'm not convinced that this actually is worth $29 million. Yeah, but it's even worse than that, because if you read the contract, you will find a function that's called set token URI. Okay, it's protected by admin required, but that just means that the guy that made this contract can do this. So even the URL can change. Yeah. But it's even worse than that, because blockchains can fork. What does that mean? Well, that's exactly what happened to Ethereum a couple of weeks ago. And now we have two chains, one that uses proof of stake, and then we have one that uses proof of work. So now your NFT is in two databases. Yeah. What happens when you sell them in one of them, right? So my point here is that there is trust involved here, and that is trust between humans. Technology can only get you so far. But there are probably some critics along you here now that will say, but there's a fix for this problem. We can avoid using regular web servers. And we can do that with a technology called distributed file systems. There's a couple of examples of this. It's also called content addressable storage. There's like IPFS and Arweave. So how does that work? Well, you take the picture file and you hash it. And you store the picture file inside the distributed file system. And the hash is a unique key that represents that picture. So you can fetch that picture using that hash. And then you take that hash and put it into the metadata. And then you hash the metadata. And then you put the metadata into the blockchain. OK, problem solved, right? Well, it's an interesting technology. And I would say it's pretty early at this stage. But what is certain is that someone has to pay to store the files. So either you have to participate by running a node in the distributed file system, or you have to pay someone to do it. There's lots of examples of like really expensive NFTs that just gone missing from IPFS. So my point here is that if you ever buy an NFT, you really need to look into the details. You need to read the contract, you need to figure out where stuff is stored, and you might even have to help out in storing the file. So basically, there's a risk that your NFT can just go missing. Okay. Let's have a closer look at how to develop smart contracts. So what would an ideal language look like for developing smart contracts? As we have seen, it is a pretty constrained development environment, right? So we need something that really fits here. So let's take a closer look. The language should be secure, which is that it should be easy to make code that's hard to exploit for malicious actors, because a bug can be costly for you and also your users. It should be simple, so it's easy to understand the code, right? So your user needs to understand your code to understand what your smart contract is going to do to their money. This is a perfect job for declarative or functional kinds of languages, right? And I say this because they control side effects and mutations, and in general, they lend themselves to be verified or proved. And then we have the imperative kinds of languages. Think of like Java or C# or JavaScript, and they have no control over side effects. They do rampant mutation, and in general, hard to reason about. And they have lots of pitfalls when it comes to security, which can cost you dearly. But you can take a little guess about what's the most popular in the blockchain world. Yeah. And the reason for that is pretty easy to understand. It's just that that's what people know and that's what they want to use. That's just how the world is. So the most popular language is called Solidity. And that sounds solid enough, right? It's made by the Ethereum Foundation, and those sit on about $1 billion in their bank account. And it can also lean on 70 years of programming language research. So that should lead to the perfect language, right? Well, let's have a look at their documentation. It is heavily influenced by C++. And I like C++ as much as the next guy, but this is not a fitting choice, I would say. The version of the language is 0.816. So OK, this is an experiment, and it's not final yet, but I'm not sure if all the users actually understand this. But it gets worse than that, because let's have a look at the changelog from the latest version. It contains a lot of breaking changes. And as a programmer, this sends shivers down my spine, right? They don't care about backwards compatibility. Whatever. Other weird stuff is they don't have support for floats. OK. But sometimes you need to divide two numbers and know what the result is. And also, they have maps, or hash maps, but there's no way to list the keys. And this threw me off when I saw this the first time, and like, why? Why? Let's have a look at that. So here we have an example. This is a mapping, or a hash map, between an address and a number. And we can use this to make a high score if you make a game. But the problem is that we can't list the keys. So we can't make a high score unless you yourself have an array next to it. So you yourself, as a programmer, need to keep the keys. So whenever you update the hash map, you need to remember to take care of the key as well. And then you can use this array to iterate over the keys and like pick out the values from the hash map. Yeah, this is just one of the many things that is off by this language here. So it's obviously under active development, right? And that's fine. They opted for a strategy for going fast and breaking things. And that's a smart strategy for getting mindshare, because after all, they are the most popular language. But I, as a developer, would not feel confident in programming in Solidity. It's just too hard. OK, it's time for the demo. This is an example of what you can actually do with smart contracts. So like I said, it's a Tamagotchi. But before I show you that, I will show you the architecture of the thing. It's what's called a DApp, or a decentralized application. And that's just a regular web page here. And it has a UI with HTML and JavaScript. And I have a library called Web3.js. And that is what I use to talk to the smart contract in the decentralized system. So this is what I'm going to show you. The demo, this is it. But usually in other kinds of dApps, you can add a backend to the mix, which is just a regular web server with a database. And usually also you have a Web3 library that can talk to the smart contract and like monitor it and do stuff when data changes. So my point here is that typical dApps, they are usually a mix, and it's not. It's usually just like the core logic and the core state that's stored in the smart contract. All right, so let's have a look at the demo. 2 seconds. All right. Okay, so I made this thing with React and 3.js, and yeah, I might have over-engineered this demo a little bit, but yeah. Currently, it's dead, right? The Tamagotchi is dead. So let's try to revive it. I'll click this button here, and you can see that my wallet pops up, and then I can see that, oh yeah, this costs 0.01 tokens, and I press confirm. Oh yeah, I need my password, of course. You don't need to see that. Let's see. Okay, and now we don't have to wait 5 minutes. This is just a test net. So usually this will go much slower. Okay. So let's see. Is this the demo effect? Oh yeah, no, he's alive. He's ready to play. Okay, so now what will happen is that time will pass, and his power will go down, and his mood will go down, and in about 10 minutes, if no one interacts with him, he'll die again, which is kind of sad. But if you can look down here, you will see a button that says withdraw, right? And only I can see that because my wallet's address is hard-coded here. So only I will see that as a developer, right? So only I can withdraw the tokens here, right? And you can try to actually invoke the withdraw function in the smart contract, but that won't work because also my address is hard-coded into that function, so it's protected, hopefully. And let's try to interact again. So I'll press the power button here. Let's try to charge him up. You can see that it costs 0.01, and I do that again, and this number down here should increase to 0.12. That is the amount of value that's inside the smart contract's wallets. Yeah, now it's charging, and yeah, exactly. So this is just to show one way that you can earn money on this. Right, okay, so that is it for the demo. Yeah, let's see. So in the end now, I just want to revisit something I said in the beginning, and that is that smart contracts are immutable. And it turns out that's not entirely true. The code itself is immutable. You can't change the code. But what do I mean? Well, let's say you have a smart contract like this. And then you discover a bug, or there's a security issue with the platform, or you just want to add a new feature, right? So as developers, we know that code is a living thing, and there will always be reasons to update the code. But how would that work? Well, we can create a new version of our code and push that out, and that will create a new smart contract. And then we will have to tell all our users to use the new address. So in my case with the Tamagotchi, that's not a problem because the address to the contract is embedded inside the JavaScript. So I will just have to update my web server, and then everything will be fine. But there might be other cases where this is more cumbersome, where you have to update all your clients somehow. Okay, so right. One thing that we have forgotten now is that your users might have interacted with the previous version and actually paid a lot of money to put state into that contract. So you as a developer then would have to copy that state. And that can cost you millions of dollars. So that's not ideal. Okay. There is a solution here which everyone uses, and that is the following. You have a proxy contract, and that's the interface that all your users are using. And the proxy contract sits on the state. So in case you want to add more kinds of variables or state in the future, you would have to accommodate for that when you create this contract to like make extra variables, which sounds weird, but that's what they do. And then the logic of the contract would be in a separate contract. So when you update, you do the following. You just push out a new version, and you have a new smart contract, and you just update the reference stored in the proxy contract, because that's just a variable. You can change that. Problem solved, right? Well, let's say this contract is a decentralized exchange that sits on millions of dollars of value. And at any point in time, using this pattern, the developers can do the following. They can add a steal method and just empty out all the value and just go away. This happens all the time, right? And it's even called a rug pull, right? So it's horrible. So once again, my point here is that you have to trust people, even developers. So technology cannot replace trust between humans. Okay, so Web3 to me is really a fascinating subject, because the distance between the hype and the actual technology is so large. We have now seen that it's not as decentralized as you'd think. The development environment has a lot of room for improvement. It's slow, it's expensive. You have to trust the developers, you have to trust centralized servers, and also something I haven't talked about at all is there's tax implications here as well. So just look forward to the day when one of your kids say, hey dad, I need some help running my taxes because I've played Web3 Minecraft. Yeah. Is this technology the future? The true believers, they say, yes, all the problems will be solved eventually. This is just technology, and technology improves. Well, they're not solved at this point in time. So in my opinion, we're still at the demo stage of this technology. And it's like a solution looking for a problem to solve. And that's a decade after its inception. But hey, who knows? Maybe they'll figure this out in the future. Okay, so I hope after this presentation that you're now better able to ask questions when people pitch blockchain-based solutions to you. If you have any questions, you can just come up to me afterwards and we can have a chat. Thanks.